All right, there we go. Hey, so guys, let me start by saying thank you. So Wednesday in class, I know that for some of you it was like bordering on child abuse, because you're like, really? We're going to do both class periods covering new material? We need a joke, right? Oh, no.
We also have another Wednesday next week.
Yeah, and so let's talk about that in a moment. So understand that the reason this doesn't happen often. There may be days, even Wednesdays or not Wednesdays, where we buy up like 5 minutes of the next period. Guys, there will also be days where we'll walk in here on second period and we're like, guys, we got a lot to do. Let's go to lab. So we do have some flexibility in both directions, but I really do appreciate you guys bearing with me. Today, in second and third periods, are going to be very different days. Guys, this material that we're going to cover today is much more approachable, it's slower, it's interesting, it's going to be a good day to slide into the long weekend. And then in third period, what we're going to do is you're going to have time to do your calculations for the previous lab, and we're going to pre-lab the next lab. So that means the next time that I will see you is Wednesday. So Taylor, to your point, so short day again, right? But this is and you guys don't even know this, but I'll explain it. This is the point in the unit where I'm sort of doing the calculus in my head and trying to figure out how to use our time most effectively. There is a little bit of chapter 4 that's still hanging in the air. Sometimes I skip it because I know we're going to come back to it in chapter 16 and 17. Sometimes I do it just because it buys us an additional day to slide into the test. So Taylor, then to your point, Wednesday we're not going to do the test. It's going to be the slide into day. It's really chill. So guys, we're looking first test next Friday. Okay. Then guys, after that first test, you typically won't get it back on Tuesday. It'll be more like Thursday. Please understand that before that Thursday, I go down to the counseling office and I tell all the counselors to not let any of you drop my class, because you're all going to fail the test. And we're going to get together on Thursday. We're going to circle up. We're going to sing Kumbaya. We're going to burn incense. And we're going to get past the fact that this is the lowest test score you've ever gotten your whole life. And then we're going to turn it into a learning experience. Quiz, not test. You're right. You did set a new standard on the quiz. You found a basement that we didn't know was there, but so I think the only right thing is to invite Sean to the table, and then we'll go on. Sean?
All right, so what happened to the tyrannical chemist?
Tyrannical?
The tyrannical chemist?
Oh, no.
He ruled with an iron fist.
Two thumbs up. That was
Chick.
So the brilliance of this is Sean takes bad content and makes it good, right?
Great delivery.
Really? Okay, so let's do this. Let's do this. In the same way that on the ACT you have scores in subsections and then you have your composite, let's vote content. Content? Wow, Sean. All right. Now delivery. All right, now the important one, composite score. See, that's... Sean, I'm going to propose that you're going to do well on the AP test because you're really good at taking garbage and making it look good. So when you get on the AP test and you have no idea what you're doing, you guys, this will be the case for all of you. You're going to be really good at polishing that turd, and it's going to turn into points. So well done. Keep that. That's an important skill to have. All right, so... Was that wrong that I said polishing turd? And I recorded it. Uh-oh.
have a graph on it.
Then that's all just done. Just as many points as it's worth, count them off. Yeah. All right, guys, questions on the homework, looking at the tail end of Chapter 4, acid and base chemistry. I think it was Elizabeth that asked last time, sort of starting this idea of how are we supposed to know? And if you remember, the one that she led us to, which was in the conceptual part of the questions, was a picture of 3 different acids. And, well, actually, one of them was an alcohol. And we talked about how are we supposed to know? So, guys, there's a very real chance that some of these are going to be how are we supposed to know? And we can talk about that. But we also understand that we are in a learning process. And so consequently, we're also becoming comfortable. Can I use the word ambiguity with you? We are comfortable with the ambiguity that says, I didn't know that before, but I'm learning as I move on. With the understanding that even when you get to the unit test, there's going to be stuff you don't know. Because you're not shooting for 100% on our unit tests. You're also not shooting for 100% on the AP test. There's stuff you're not going to know. So with that said, questions? Now we want to know, because we want to learn as much as we can. Go ahead, Ivan. It does not. Yeah, let's talk about your statement, and then frankly, I need to get 31? Oh, thank you. Okay, so hold on. So you said bases give away hydrogens, and that's actually not true. It's the opposite. Bases take in hydrogens. So let's look at the two, guys, this is important. Let's look at the 2 ways that can happen. So with the understanding that bases take in hydrogens, where do the hydrogens come from? The acid, which in many times is water. So Ivan, let's look at a couple examples. So for example, we talked about the idea of NH3. That's a weak acid. So what that does is it attacks water. And when it attacks water, it takes in a hydrogen and it leaves an OH. And as a result, we take in the hydrogen and we're basic, right? But guys, this actually happens here too. This is weird. Weak base, thank you. So guys, this one's weird because we understand that sodium and hydroxide break in, they're strong electrolytes. It's a strong electrolyte salt. So when we put those in water, they exist as ions, sodium and hydroxide. But we've talked about the idea, this is strange, but watch. We've talked about the idea that bases take in hydrogens. But this appears to violate the rule, right? But it doesn't. And here's why. It's stupid, but here it's not stupid, it's weird, but this is the idea. Remember that this is happening in water, right? So if this is happening in water, what happens is the OH grabs a hydrogen from the water. But what are the products of that reaction? The exact same thing. See what I'm saying? So this OH is in fact basic. It takes in hydrogens from water, but then the trick is when it does, it just makes more hydroxide and water, and we're back where we started. But that chemistry is actually taking place. It's just the products are the same as the reactants. Yeah.
So is a base formed technically because it received a hydrogen or because it formed an OH? Or does it have to have
The word, Clara, that I'm hanging on is formed. So bases are not formed by the chemistry that we're talking about. They're defined by the chemistry that we're talking about. So this is the base. It is a base. The reason that it's basic is because it's better at taking away hydrogens than water. So NH3 is the base. So this takes the hydrogen from the water, and then the thing that's formed is actually a conjugate acid. So we're not, and sorry if I'm making too much of the word formed, redirect my thinking. But when I hear the word formed, I'm thinking, what turns something into a base? And what we're really saying is, what is a base? And the idea is that it's something that takes hydrogens and protons, typically from water.
Correct.
Is that okay?
The thing that defines it as a base
Yes.
is the receiving the hydrogen, not the creation of a base.
Correct. Yes. Wow. Really well done. But I want to tag on to that. So did you guys hear what Clara said really well? She said, the definition of a base is the receiving of the hydrogen and not the production of OH, right? And the answer is yes. But here's the thing. In general chemistry, because I know this seems big and hard, but this is a very small tip of a really big iceberg, most of the chemistry that we're going to do in here will be aqueous. Because it's aqueous, we're always going to have water, and because we're always going to have water, we're always going to make OH, right? What you're going to find is that during your sophomore year in chemistry, you will talk in organic chemistry, and you will radically expand your understanding of acids and bases. Because in organic chemistry, a lot of the chemistry doesn't happen in water. And when that happens, it really is about the gaining and losing of hydrogen, but the source of those hydrogens is not water. And as a result, you need that bigger idea. But then you'll find out in organic, it gets even worse because you can have acids and bases with no hydrogens at all. Either the acid or the base, and then you get into what's called the Lewis definition of acids and bases. And let me show you an example. So, and guys, this is not just me throwing fluff. You're going to need to know this, not for this test, but in chapter 16. So let me show you. So NH3 looks like this. And so if we have a water molecule, is it okay if I write it like that? So we've got the OH and then the hydrogen ion. It'll become an ion when that breaks, but functionally it's going to be a proton, right? So what the base does, the NH3, is it accepts this proton, and then this is left as OH minus, and then we get that bond, right? So that's base, hydrogen acceptor. It turns out that in the eye of an organic chemist, it's not about the accepting of the hydrogen, it's about the sharing of electrons. And so there's a whole other definition of acids and bases. They're called Lewis dot structures, right? Lewis was an electron freak. And so in organic chemistry, we don't keep track of the nuclei, we keep track of the electrons. And so in the Lewis definition of a base is not a proton acceptor, it's an electron donor. And at that point, everything has electrons and anything can be seen as an acid-base reaction. That's when you're going to want to drop organic chemistry because it gets so hard. Yeah, because you start drawing what are called electron pushing diagrams, and you actually have to track all of the electrons. They're usually in blue. I don't know if I'll find one immediately. Anyway, they're called electron pushing diagrams, and you actually have to track all of the electrons, I don't see one, through all of these reactions. It's horrible, yeah. My son is taking it in a week, and he's going to die. So, all right. So, guys, other questions? Ivan, did we do good on you? Okay, what else, y'all? 30, you said? Just 30? Here, let's just read through it. The whole thing in general. Okay, so let's have story time. So it says, which of the following solutions... Oh, you know what? Let's dig into this. Guys, question number 30. You're going to see a lot of questions like this on the test and the AP test. And you guys understand this, right? All of the questions that you're going to see on next Friday's test come off of old AP tests. You guys understand that? Now you know. So guys, on the AP test, they love to ask you questions that come at multiple pieces of thinking in one question. So guys, let's look at number 30. So what we've got is this. We've got I was trying. Okay. So guys, looking at number 30, here's what we've got. We've got 0.6 molar NH3. Sorry. We've got 0.15 molar KOH. And then we've got 0.1 molar BaOH2. So, guys, and I'm going to clean this up because that's not helping us. Okay, so 0.6 molar NH3. So, guys, let's do this. Strong or weak base on the left? Strong or weak base in the middle? Strong. Strong or weak base on the right? Is it? Oh, it is. Yeah, it's below the line. For some reason, I thought barium was higher and not soluble. Okay, so well, that was stupid. Why is what I just said stupid? If you didn't hear what I said, I was thinking, wait, I thought barium was higher up on the periodic table and therefore not soluble. Why was that dumb? It's got a molarity. It told me straight out the chute it dissolves in water, but in my brain I was like, wait, maybe it doesn't dissolve. That was dumb because it's got a molarity. So now we need to talk about how these break apart. And guys, what we're looking for, Elizabeth, isn't it saying which is the strongest base? Okay, so most basic, good. So which is the most basic? So what is going to make it basic? How much OH we've got. So strong base completely breaks apart. What will be our molarity of OH? 0.15. Also 0.15 molar in potassium ion, but we don't care. Now guys, we go over here. 0.1 molar in BaOH2, but when this breaks apart, what do we get? 0.2. Right, 1 Ba, 2 OHs, doubling the concentration of OH. Now guys, this is 0.6 molar, and this is where you're getting into something that you don't know, but we do need to talk. This is a weak base, so we will not have 0.6 molar OH, because remember, we've got the NH3 attacking water, and when it does, it reaches equilibrium with hydroxide ion and ammonium ion. But the problem is you don't know which side this equilibrium lies to. I do know because we're going to calculate it in chapter 17. So let me tell you. Guys, it's slightly less than 5% ionized. So only 5, and we'll get the number for real in March. But guys, it's less than 5% ionized. So 95% of this stays as NH3. So 5% of 0.6 is less than either of those two numbers. And that, therefore, is backwards order of basicity. These weak bases are really quite weak. What's that? Well, here's the thing that's really weird. This is a relatively strong weak base. Other weak bases that we'll work at are powers of 10. Are you familiar with orders of magnitude? Do you know that term? So a power of 10 is an order of magnitude. They can be 6 and 7 orders of magnitude weaker. Yeah, so you're looking at molarities in the 0.00001 molar range. So they're quite low. So, Elizabeth, was that okay? No. No, so let's do this. I'm going to repeat that thought back. So Elizabeth is saying, if I thought that it was 0.6, it's something that I didn't know. So I'm not trying to be offensive, but the answer to your thought is no. If you thought that the concentration was 0.6, it means that you didn't understand or see that this is a weak base. Weak base means it doesn't completely break apart. So if you thought it was 0.6, there's a gap in your understanding. If you knew that it was less than 0.6 but didn't know what, you're fine. But if you thought it was 0.6, there's the gap. Is that okay? Taylor, go ahead. Well, sort of. So, but then we're using two terms interchangeably. So when we talk about conduct electricity, the term that we use is electrolyte, right? But when we talk about bases, the overarching thought is right. This doesn't conduct electricity very well, but instead of us calling it a weak electrolyte, which is true, we think of it as a weak base because that's the context. So all weak bases are weak electrolytes, but there are other weak electrolytes other than bases. So that's where things get interesting, because actually NH3 is a pretty good base. The reason that NH3 is a pretty good base, so like for example, if you were to take NH3 and react it with hydrochloric acid, what you actually end up with is NH4 plus chloride ion. But here's the trick. That arrow is correct. It is not an equilibrium process. The reason is as soon as you introduce a strong acid to the chemistry, that strong acid beats the crap out of this weak base. So this will go to completion. So NH3 is going to function as a functional base because HCl is just going to start dumping hydrogens on it. And this one will go to completion. There will be a limiting reactant. Yeah. What else, y'all? You guys okay? Yeah.
Well, like something we're asking, like to identify if it's like a weak base or stuff like that. I know like all the strong acids, but I don't know how to tell something.
Yeah. Can you lead us, Michael, to the one you're looking at?
I think it's on 35.
Okay. So, guys, let's talk generalizations. Say it again, Linz.
I just wrote my paper like forever. How do you know?
Yeah, I know, right? Okay. Is 35, is it just that? Okay. So guys, let's talk. Let's do all of them, but I want to skip letter B. We'll come back to it. And actually, Claire, you're going to find out that our conversation, well, as everyone's conversation, this is going to be important. So guys, are we okay with the idea that HF is a weak acid? Okay, but if you're not sure why, and this is interesting, again, we'll talk about it in chapter 16. Guys, notice, HI, strong or weak acid? HBr? HCl? HF? Right, weird, right? It seems like we have a trend in the halogen-containing acids that these are getting, they're all strong. Well, guys, it turns out that they actually get stronger as we go down. And HI or HF is weak enough that it's not even a strong acid. Let me give you a flavor for it, and we'll talk later. The reason is because the bond that forms between the hydrogen and the fluoride, remember fluoride's the most electronegative element on the periodic table. Guys, that bond is so strong that it doesn't break readily, and as a result, it's a weak acid. Yeah?
So, you said it leads strongly.
They do.
But a strong acid is an acid that dissolves completely.
Right, right.
Dissolve completely.
Yeah, it's a good question. How can you be more complete than complete, right? So let me try this. We'll talk in chapter 16. But the idea is this. I love what you're thinking, that you can't be stronger than complete, right? But there are still ways that we can measure, quantify I don't even have a word. The ability of these molecules to release hydrogen. And we know that they all do it completely. And I don't want you to have the thought that this is about rate, like HI gets rid of hydrogens faster than HCl. But there is still a way, and we don't know enough to talk about it, but there is still a way that we can measure the probability. The word we actually use is propensity. Is that a word, you know? So just let's go with how well it does this. And so now we've talked about it, so we've got to talk about why. So why is it that at some level, they all go complete, right? I, B, R, and Cl, they all go complete. But why do we say that I is better? And the reason is because I is bigger. So if you think about it, chloride is first and third energy level. So 1s, 2s, 2p, 3s, 3p, right? So at that boundary of the third energy level is where that covalent bond exists. And it's relatively strong because the nucleus of the chlorine and the nucleus of the hydrogen are relatively close together. But then when we go down to bromine, we've got all sorts of weird stuff going on because now we have a D sublevel, which is an absolute mess, right? And it's even bigger. So now when we've got bromine, we've got a physically larger atom with way more interference and shielding. And so the bond that bromine forms with hydrogen is physically weaker. Because it's physically weaker, it's more likely to break. Eventually they all break completely. But there's a rule that says the bigger the thing the hydrogen is bonded to, the stronger the acid will be. And we'll talk about those trends. Yeah.
So what about astatine?
About what?
Like hydrogen with astatine, since it's also
I'm not sure what astatine is.
AT.
Oh, AT. Oh, I'm sorry.
I don't know.
No, I get what you're saying. That's a really interesting question. Right, because when we get down to like francium and radium, we don't think of those as being strong bases because they are so unstable. This is a guess, and it's a complete guess. But so it could be your thought that maybe it's radioactive and unstable. My guess is that astatine has such low earth abundance. We actually talk about how much of this stuff we can dig up on Earth. And I suspect that astatine has such a low earth abundance that we don't think of it as a strong acid simply because there's not enough of it hanging around that hydrogens can actually get with it in a large enough quantity to consider it a thing. That's my guess. If you're curious, look it up and let me know. Yeah, like why, and don't do it now, but why don't we consider HAT a strong acid? And I don't know. Go ahead. Oh, it's safe to assume that 90% of the stuff we talk about in here you'll never see, even as a chemistry major finishing up your degree. Yeah. Oh, yeah. No, absolutely. Yeah. I mean, if you know how our stockroom is huge? Literally, we touch about 5% of those bottles. Yeah, we could literally take my stockroom and fit it inside this cabinet, other than the fact we have to spread them out. And most of those chemicals were bought in the 1950s. And yeah, back when we could buy dangerous things. Okay, so back to the question. So, weak acid, yes?
Yeah.
Skip. This guy?
Yeah.
Salt. Right? 2 ions, that is a salt, so it exists as ions. And then, guys, finally, this barium hydroxide, strong base. Okay. Now, guys, this, what about letter B? And so Lindsay is sounding the battle cry of Elizabeth, which is, how are we supposed to know? You wrote it down how many times? Oh, okay. So guys, this is the deal. This is one thing that you should tuck away in the back of your noodle. And actually, the best place to do it is right here. This molecule is NH3CN. Okay, so it actually looks... So NH3CN, it goes NH3 or 2?
CH3CN.
Oh, thank you. I'm like, that can't exist. I was trying to write the Lewis dot structure for it, and I'm like, that does not work. Okay, there we go. So C, H's, is that right? CH3, C, and N. That's actually what it looks like. But guys, let's talk about this. NH3 looks like this. Guys, NH3 has no bonding sites. Why does it get to act as a base? Why does NH3 function as a base? Go ahead, Jared. Yes. So, and we've been thinking about this in the context of water, but whatever. So the idea, guys, is that this, wow, my board, this hydrogen ion is a proton and it globs onto there. Yes? If we were to bring water into this picture, same thing. Nitrogen has 2 unbonded electrons. You'll find out later we call these regions of increased electron density. But guys, this region of increased electron, there's a lot of electrons there, is wildly attractive to hydrogen ions, which are protons. And we have a bond forming there that is not truly a covalent bond because hydrogen doesn't bring an electron. It leaves it with the water. And so this bond that forms makes this a base because a proton, a hydrogen ion, goes to the nitrogen. Guys, that's how these nitrogen-containing compounds function as a base. So, Lindsay, general principle, if you see nitrogen in a compound, you are thinking weak base. Okay? Every time. That's the only one you need to know right now. If you see nitrogen in a compound, you immediately go weak base. It is. It does, and the thing that I really find fascinating, diatomic nitrogen, that is the strongest bond found in nature. Isn't that weird? That this is the high watermark for bond strength, the triple bond that exists in nitrogen. Yeah, there's other triple bonds, but that's the strongest we got. Yeah, that's neat. All right, you guys good? Let's be done. All right, so gang, note stuff, no calculators. You can put away your books. Cleaning this up. So guys, this is where I need to call on you to help me. So this is what I need from you. I am going to recording, kaboom. Oxidation reduction. So guys, here's the deal. The next time these 2 words appear on this screen, we are 3 days away from the end of the content year, moving into spring break, and getting ready to prepare for the AP test. And that's going to be here in like a matter of weeks. I know it's 8 months, but it's going to feel like a matter of weeks. It goes so fast. So guys, in the same way that we did a 30,000 foot view of acids and bases, just enough that we can talk, but not enough that we understand, guys, we are doing the same thing here. This is chapter 20. It's the very last thing we're going to do this year, but we need a 30,000 foot view. So guys, I'm going to give you the fundamentals. We're going to talk about some important points. You are going to be doing this chemistry when I see you on Wednesday. But guys, for now, we just need to define some terms and we need to look at some chemistry. This is 1, 2, 3 slides long, not including Babs. Are you guys beginning to feel sort of like a connection with Babs? Somewhere? Okay. All right, so guys, definitions. If any of you have siblings or maybe friends that are serving LDS missions, guys, if you've talked with these people, you know that there comes a moment in time where, missions in other speaking lands, right? Not English. So, and if you think about it, it's kind of miraculous. In a matter of weeks, these kids learn to speak languages well enough to share important things. It's kind of crazy. But guys, there comes this moment in the life of every foreign-speaking missionary where they would tell you that they knew for certain they had internalized the new language. When is that? Not thinking. Dreaming. Yeah. Guys, they will tell you that I knew that I finally learned Italian because I was dreaming in Italian.
I can dream up to 5
So you know the joke, right? What do they call somebody that speaks 3 languages? Trilingual. What if they speak 2 languages? Bilingual. What if they speak 1 language? American. Yeah. I have friends that are actually, they live in Belgium, and even their youngest, who's like 12 now, speaks 6 different languages fluently. Yeah.
That's not like a standard. That's
No, but it is in Belgium. They actually have 3 official languages for their country. Yeah, it's really interesting.
It says 2 official languages in 10 major regions.
See, exactly.
And of their minority
So guys, all of this to say, you are not going to dream in oxidation reduction yet. Here's what's going to happen. And this is me trying to speak Spanish. If I want to try to speak in Spanish, I know a little. I have to think it in English, translate it in my brain, and then hope it comes out okay. Guys, you're going to be doing the same thing here. When you think about the word oxidation, you are going to have to think and go, wait, mental picture, what does oxidation look like? But guys, in chapter 20, you're going to get so immersed in this that it's going to become your primary language, that you're not going to have to translate. You're just going to be able to go, oh, I know what happened to this atom. That guy got oxidized, without translating. But for now, let me give you the translator. Guys, oxidation refers to the loss of electrons by a substance. So if an atom or a molecule, mostly atoms, sometimes ions, if an atom, we'll say, loses electrons, that guy is going through oxidation. Not surprisingly, when this happens, the charge becomes positive. So guys, here's an interesting little tie back. Why do we call this oxidation? And the reason is because it's based on what word? Oxygen. And guys, remember what we know about oxygen. How many valence electrons does oxygen have? 6. Crazy electronegative, right? Second only to fluorine. Guys, oxygen is it's a little electron grubber. It's really electronegative. It's got room for 2 electrons, and oxidation just runs around and steals electrons off of things. You guys understand that when we send the Artemis rocket up to the moon, we were supposed to last week, but we had some problems. Guys, there's a tank of liquid oxygen in that thing, and that oxygen just rips the crap out of the fuel. I don't think it's kerosene, although a lot of rockets are. And guys, you've got an oxidizer, oxygen ripping electrons off of whatever the fuel is, and that releases so much energy that rockets go to the moon. Because these are violent reactions. But we call it oxidation because when they originally started doing this, 100, 200 years ago, they were noticing that oxygen was really good at ripping stuff apart, specifically metals. So now guys, think about that. What do we know about metals? Big or small? Weak or strong? Weak. They give away electrons, right? And so they found out that metals, wait for it, sitting outside tend to lose their electrons. Where do they go? Oxygen. What do we call it? Rusting. Guys, that's all it is. Rust is actually just oxidized metal. When your car frame rusts, it's made of iron, and it turns into iron oxide. That we call rusting. So, guys, the other direction is true as well. We've got reduction. Reduction is the gaining of electrons, and not surprisingly, the charge becomes more negative. So guys, here's the weird question. If oxygen causes oxidation because it takes in electrons, then why don't we call the gaining of electrons something like sodiumization? Because sodium gives away electrons like crazy, and it can cause somebody else to take in electrons, so why don't we call it sodiumization? Well, guys, it turns out lots of other things can give away electrons, so why do we call it reduction? Why would they call this reduction? It's the reducing the charge. So guys, literally they call this reduction because the charge is going down, which leads us to a little interesting mnemonic that you can use. The charge of the particle being reduced is reduced. Or, if you happen to know somebody on the BYU chemistry faculty, over at BYU, they say this. They teach all their students oil rig. Oxidation is loss, reduction is gain. Do with that what you will. But guys, again, here's the thing. This is like you being introduced to a language. You're going to have to translate. By the time we get into chapter 20, you're just going to go, oh, look, that atom came out of solution, and it was being reduced as it was plated out onto an electrode. I know that meant nothing, but we're going to become much more conversant with this. So, guys, moving forward then into the chemistry, guys, think about this. What does oxidation do? Lose electrons. What does reduction do? Where do those electrons come from? The thing that's being oxidized. Guys, the deal is this. You can't have oxidation without reduction, and vice versa. As a result, skipping through... Oh!
Yay!
Why do you always make fun of my pain? Guys, moving through oil rig, these are called redox reactions. Yeah. So, guys, when you hear redox, this is what chemists talk about. They don't say oxidation reduction. We say redox. Guys, redox reactions, then, are an exchanging of electrons. Some of you are now thinking to yourself, wait, isn't that kind of like acid-base? Because acid-base is a change of a proton? No. There is an exchange, but don't try to make too many connections. So guys, redox reactions are reactions where electrons are exchanging between substances. So guys, the question then becomes, so oxidation reduction is the exchanging of electrons between substances. Now guys, here's the trick. How do we know acid-base chemistry is happening? We can literally track the protons. But guys, how do we know that oxidation reduction chemistry is happening? Guys, electrons are probabilities, right? How do we know they're moving around? And the answer is the same way that we know black holes exist. Guys, you understand this, right? We've never seen a black hole. Well, we got a weird picture, and actually if you've seen the Derek Mueller video of what that picture actually means, it's fascinating. But it's not truly a picture of the black hole. Right. So guys, in the same way that we can't see black holes, but we can see the influence that black holes has on the space and around them, Guys, similarly here, we don't see electrons move, but we look for evidence. And the evidence that we look for is changing of charges, which we call oxidation numbers. So guys, this then leads us kind of smoothly into the first skill that we need to gain. How do we identify oxidation numbers? Because if we can figure out the oxidation numbers, we can then look for change, and then we can look for oxidation reduction. So the question then, guys, becomes how do we do this? And then this is actually the last of your notes today, and then we're just going to fiddle with a couple examples. So what does it look like to assign oxidation numbers? These are the rules. Number one, all atoms in their elemental form have an oxidation number of 0. Guys, just write this down. Elemental form 0. That's all you need to write. I don't think this is going to work. Oh, it did. So guys, number 2. Don't write it down. Don't write it down. Let me show you what this means. This is going to become really, don't write it down. The better thing to do is write the example. So, guys, let's look at some familiar friends. This you do want to write down. Uh-oh. Quit. Mila, I'm going to make you get up here and run my board for a couple minutes. And then you will be able to empathize rather than just sympathize with my pain. Actually, that's true. She's causing my pain.
Anthony says that we would all have to start laughing at her if she went up there.
It's actually a good point. All right, so guys, do this with me. Sodium is +1, chlorine is -1, but wait, how do we represent that? We go 1 plus and 1 minus, or we can drop the 1 and just go plus or minus, but the ones are like this. Now guys, stop. Water is H2O. Oxygen's -2, hydrogen's +1. But it goes like this. Do you see the difference? Well, there's two hydro. Okay, so let's, if this example is distracting, oops. If this example is distracting, then let's do something different. You can write this one down with me too. CaCl2, 2 plus, 1 minus. Correct. The order is different. So guys, these are charges and these are oxidation numbers. So let's talk about the difference. Calcium chloride. What kind of compound is that? It's a salt. So what kind of bonding does it exhibit? Ionic bonding, because literally 2 chlorines have each lost 1 electron to calcium. So this now has a, other way around. 1 calcium has lost an electron to each chlorine. These are charged species. So these are the charges. When we write charges, it's number first, charge second. But guys, this is not a salt. What is it? It's a molecule. Hydrogen does not have a +1 charge. Oxygen does not have a -2 charge. So what do those numbers represent? Not the number of electrons they've lost. This is covalent bonding. It's the number of electrons they have shared. Those are different. And you'll notice we write them as +1 and -2. So if the number comes first, it's an ionic bond and a charge. If the charge comes first, it is a covalent bond and is an indication of the number of electrons they're sharing. Does that make sense? Okay, so with that said, on the AP test, they will not hold your hand to this fire. If you were to write down sodium chloride, don't write this down with me, but if you were to write it down as +1 and -1, technically that's wrong, because they're charges and they're not sharing. But they will not hold your hand to this fire in this, I won't either, in here or in AP. So then, guys, the question becomes this. What on earth does this mean? And what it simply means is that for most atoms, the number of electrons that they lose is equal to the number of electrons that they share. So let me show you an example. Calcium oxide is a salt. Calcium oxide is a salt. So what is the charge of calcium? 2+. What is the charge of oxygen? 2-. Here it is gaining 2 electrons. Here it is sharing 2 electrons. So the number of electrons that they share and the number of electrons that they gain or lose are the same most of the time. But in here we're going to say it's always the case. Do you get the difference? In college they will hold your hand to the fire. In here, that's what that's all about. Okay, so then, oh, wait. Mila, hush. Ah. So guys, nonmetals typically go negative. You could just write down nonmetals negative. But that makes sense, right? They're on the left, on the right side, they're electron gainers. Nonmetals negative. Then guys, hydrogen, we talked about this last year. This one's worth writing down in its entirety. Hydrogen goes positive when it's bonded to a nonmetal and negative when it's bonded to a metal. Hydrogen, like Paul, is all things to all people. If hydrogen is hanging out with a metal, it's going to act as a nonmetal, and it'll take in an electron. If hydrogen is hanging out with a nonmetal, it will act as a metal, and it will give an electron. So hydrogen is flexible. It's like, hey, you do you, and I'll adapt. Then, guys, the next one, the sum of all the oxidation numbers in a compound is 0. You could just go oxidation numbers, compound, wait, sum is important. Sum, numbers, compound, 0. And then guys, finally this and that, oh, Claire, you?
Yeah. How come it's usually only nonmetals? Like, is there a time when nonmetals are common?
Hold on, which one are you, is this just a general question or?
The third bullet, like why is it usually?
Oh, good question. So the idea is this. So nonmetals are the dudes on the right, right? And so most of the time so do you understand that this class is technically inorganic chemistry? So this is the chemistry of not carbon. So it's really, seriously, and so it's the chemistry of salts and solutions and things like that. And so in that context, frankly, we don't deal a lot with molecules. We do very, very little molecular chemistry. Consequently, we're thinking about salts. And when we're thinking about salts, we're thinking about the nonmetals being electron taker-inners so that they can form salts with the metals. And so because of the context of what we're doing in here, we typically treat those as being negative, simply because we're thinking salts. In the instances where we're thinking of them in molecular structures, then we're less concerned about their oxidation numbers, because what we're actually doing is just drawing their Lewis dot structures. And at that point, we really don't need to know that oxygen is -2. What we really need to know is oxygen's got 6 valence electrons. So does that make sense? Yeah, that's the distinction. So guys, then finally this. The sum of all the oxidation numbers in a polyatomic ion is the charge of the ion. So you could write down sum numbers polyatomic charge. So guys, by the end of the day, do you feel like your brains are like ready to explode? Lots of stuff, right? Haven't learned a thing. Yeah.
Sometimes, like, during class, like, okay, like, I understand that. I can't go.
Yeah. Right. Yeah. And that's, yeah, right. And understand that's normal. But the trick is that eventually you just become so immersed in all this content that you start to realize that you're actually thinking like a chemist. It takes a while, but it's also why cramming in college doesn't work, because the expectations in college is that you're fully immersed in the content, and if you're cramming, you never get to that point. And so, you know, we have 9 months, right? And by the time we get to May, you're going to have a little chemistry brain inside of you, right? Right now you don't. And so, yeah, I had that experience when I started teaching AP, because general chemistry has nothing to do with AP, right? And so I had taught general chem for a decade. I was 10 years out of college, and then all of a sudden I'm like, oh crap. And it was amazing to me how much of the material I remembered from college simply because I was soaked in it in college. Yeah.
You ever dreamed about chemistry?
I've had dreams about strangling chemistry students. Is that in any way related?
Or do you dream in oxidation reaction?
Yeah.
Maybe you should have turned out the recording before saying that.
Oh no, that's okay. I didn't name names. And what's that? No. A lot of them are still here at school. Okay. So guys, moving along. Give a couple spaces. Drop down a couple spaces. Write this down somewhat big. We're going to play with it. So guys, all of these things are now going to come to bear on this example. So this, did you guys need to memorize Mno4, the ion Mno4?
Yeah.
Permanganate? Okay, -1 charge. Okay, so guys, this is the salt potassium permanganate. Interestingly, you do need to know that it's purple. It's actually this, and so this is potassium permanganate in its solid form. You may or may not remember that last year we made solutions of it when we talked about when we talked about molarity. Anyway, so guys, the question is this: we need to know the oxidation numbers for each of the substances in this. Each of the atoms in this compound. Here's how to approach it. Do this with me. So guys, the first thing that we need to realize is that this is a salt, and it will split there. Now, When it splits there, what is the charge of the potassium? Potassium's charge as a group 1 metal is 1. Now, is it 1 plus or plus 1? 1 plus, because this is an ion in solution. Again, if you put plus 1, they wouldn't mark it wrong on the AP test. I won't mark it wrong. They'll get you in college. Now, guys, what is the charge of the Mno4 ion? -1. But do this with me. Write that high above. Oh, not like that, though. You guys lied to me. It's 1 minus. So now, guys, let's do this. What does the Mno4 actually look like? It's a molecule. Now, guys, I can't draw the Lewis dot structure for it for you because you don't know about octahedral domain geometries and square planar molecular geometries, because in your little world, the octet rule is a barrier. This thing actually has 12 valence electrons, and it's a mess. We'll talk later. To make general chemistry something that doesn't blow your mind. Well, I know, that's why you're here, right? Because how many times did Miss Call tell you, we talk about it in AP, and now you're here, right? Yeah, we'll talk about it later. This is later. So, guys, this is the deal. This is a molecule. Guys, this is not its Lewis dot structure. Okay. This is actually its Lewis dot structure. It has 2 sets of valence electrons sitting in the y-axis, and then all 4 of the oxygens are actually in the xz axis, and it actually forms something that's planar and square. We'll talk more later. So, guys, with that said, these are covalent bonds. So, will the manganese and the oxygen have charges or oxidation numbers? Oxidation numbers. Now, oxygen is our fixed point. Oxygen is -2. Now, guys, look at manganese. Not magnesium, manganese. Element number, you can't even see it, and your periodic tables are worthless. But, guys, if you look at manganese, manganese can go 2, 3, 4, 6, or 7. So which one is it? And, guys, yeah, here's the idea. We've got 4 minus 2s. That's -8. But the overall charge is -1. So that means that this is +7 because the oxidation numbers of all the atoms in a polyatomic add up to the charge. Is that okay? Now, guys, this. If you had written +1, 7 plus, and 2 minus, those are wrong, but they won't get you for it. They will not hold you accountable for formatting. You just got to get the charges and the digits right. Go ahead, Sean.
So you said that the oxidation states are equivalent to the number of electrons shared.
Correct.
But if each oxygen shares 2 electrons, then what does manganese only have the 7?
Yeah, and the reason is because what happens to this down the road. Because, and again, we can't draw the Lewis dot structures yet. This is unstable. Mno4 without a charge is unstable. What the Mno4 has to do to become stable is it needs to take this electron from the potassium. What you'll find out, and again, we can't do it yet, Mno4 without that other valence electron has a double bond that bounces all the way around the molecule. And that makes, it's called delocalized pi bonding. And so that bond is relatively unstable. So what happens is as the electron from the potassium falls into this molecule, it actually allows that double bond to settle down into a single bonded structure, and it stabilizes the molecule. And so the idea is that when we talk about permanganate, we only talk about it in its 1- form because that stabilizes it. Yeah, great question. You guys good? All right, so what are we going to do about this? Oh, Mila, go ahead. It makes it, normally you laugh behind my back. It makes it better when I can look you in the eye. It makes it more tolerable. Okay, so guys, don't write this down, but this is what you need to know. Most oxidation reduction reactions are single displacement reactions. Can you picture single displacement in your little brain? We have an element, we have a compound. If the element is a metal, it grabs the non-metal. If the element is a non-metal, it grabs the metal, and whichever one didn't get grabbed gets the boot, yes? Okay, so guys, what we're going to do is this. Why is that there? What we're going to do is this. First of all, we are going to talk about this by acids. So write by acids. So here we go. Leave yourself space. Zinc, hydrochloric acid. Some of you remember doing this in lab, where you put the couple pieces of zinc into a test tube with 6 molar hydrochloric acid. You inverted a test tube over the top. You collected the hydrogen gas that was released. You took a burning popsicle stick, you inserted it, and it went boop. And you chuckled and did it 7 more times. So guys, what we need to do is this. We are going to predict the products, kill our spectators, write a net ionic equation, and then talk about oxidation reduction. So guys, let's do our let's do our balanced equation first. Zinc, positive or negative? It's a metal, and even on your worthless periodic table, you know that it's a metal, so it's positive. Guys, actually, this is one of them that you need to know. Elizabeth, go ahead and say it. How are we supposed to know this? Because we're learning as we go. Zinc, when it hooks up with chlorine, is +2. Chlorine is -1. So our first product is ZnCl2. Then the hydrogen gets the bootski, and it goes diatomic. Now at this point, we need to balance this, and we're done. Okay, now what we need to do is we need to assign, oh, go ahead. Let me answer that in a second. We're going to get to an interesting thought, and it ties to what you're saying, but I don't want to say yes, because I want to get deep before we can, So guys, now what we need to do is we need to assign oxidation numbers. So be careful. We know that zinc goes +2 when it bonds to stuff. But guys, when zinc is chilling on its own, its oxidation number is 0. This is what it means when you wrote down the oxidation state for atoms in their elemental form is 0. Now do this. Hydrogen is bonded to chloride. So the hydrogen is sharing an electron, the chlorine is sharing an electron, but the chlorine is the more electronegative, so the chlorine is going -1 and the hydrogen is going +1. But we already knew that hydrogen was +1 and chlorine's -1. And guys, if you had written this 1 plus and 1 minus, that's fine, because we're saying that they're the same, understanding they're technically not. Now when we get over here, chlorine is still -1. Well, actually, you know what? I should do this technically correct, even though it doesn't matter. It's technically 1 minus, because now it's ionic. Then, guys, this. What is the zinc? 2 plus. Now, Clara, to your question. What about the hydrogen? The hydrogen is 0. Because this is hydrogen in its elemental form, which kind of gets to your thought. So guys, for the diatomics, iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen, for the diatomics, their elemental form is diatomic and therefore it's 0. Is that okay? All right, so now guys, let's kill our spectators. Done. And now let's bring down our net ionic equation. Zinc, 0 plus 2 protons yields zinc, 2 plus, and hydrogen molecule 0. The spectator is anything that doesn't do chemistry. So these chlorides started, remember, because when this is actually acid dissolved in water, right? So what we actually have is protons and chlorides, so they didn't do chemistry. All right, so now guys, do this with me. Draw an arrow about a line below connecting your zincs, and then draw a line a little bit lower connecting your hydrogens. Now guys, turn your attention to the left. What happened to zinc? Did it gain or lose electrons? Lost electrons, because it goes from 0 to plus 2. Is that oxidation or reduction? That is oxidation, the loss of electrons, and specifically, that was the loss of 2 electrons. Now guys, watch this. Hydrogen goes from plus 1 to 0. So it gained electrons, so it was reduced. That's reduction. But, I'm sorry? No, because it goes from plus 1 to 0. So if it starts at plus 1, picking up electrons makes its charge go down, so that's reduction. See how right now we're kind of like in the MTC, we're having to think through things? You'll see that when we get to May or to April, you can be like, oh yeah, I get it. Now guys, wait, how many electrons? Well, we went from plus 1 to 0, so that's 1 electron, but it happened twice, so it's a total of 2 electrons. Guys, you're going to find out in chapter 20 there is a law of conservation of electrons. Those have got to balance. So now, guys, I want you to do this out loud with me. What substance, and I really want words to come out of your mouth, what substance was oxidized? Zinc was oxidized. Zinc lost electrons. What substance was reduced? No. Hydrogen was not reduced. Guys, hydrogen is a diatomic gas. This is not hydrogen. These are protons. Protons are not a diatomic gas that we can fill balloons with. So this isn't hydrogen. What is it? Hydrogen ion, and those aren't the same. Good? They couldn't be more different. In the same way that chlorine is mustard gas and will kill you, and chloride is delicious on your fries when it's with sodium. They couldn't be any more different. Guys, we're going to do one more and we're going to call it a day. Salts. Zinc plus copper 2 sulfate. So this is not acids, this is salts. So guys, we're doing zinc again, but now it's being attacked by a salt. Double displacement reaction. We get zinc sulfate, and copper gets the bootski. So now guys, let's make our lives a whole lot easier. Does copper 2 sulfate dissolve in water? You probably don't know the sulfate rules, but the answer is yes. Does zinc sulfate dissolve in water? You probably don't know the solubility rules, but the answer is yes. What you're going to find out is that that makes sulfate a spectator, so let's kill it right now. Then guys, this, what is the charge of zinc in its elemental form? What is the charge of copper in its elemental form? 0. What is the charge of copper when it's bonded to sulfate? Well, sulfate's -2, so copper is 2 plus or +2. Same thing here, bonded to sulfate, zinc is also 2 plus. This is then our net ionic equation. So guys, questions. How many electrons are being exchanged? How many electrons does zinc lose? 2. How many electrons does copper gain? 2. What is happening to zinc? Oxidized or reduced? Oxidized, losing electrons, charge going up. What is happening to copper ion? Being reduced because its charge is going down. Its charge is being reduced. Do you get the idea? Okay, so guys, here's what we're going to do. This, Mila? It's losing its novelty. Here's your homework.